No problem, sir. Thank you very much.
Okay, let me share my screen. Let's start the session for the day. This is the last uh, session that we'll have in this course from me, and it's a very interesting topic. Uh, there are a couple more topics. Unfortunately, I couldn't cover. I said I will record those topics and share with you. I will probably do that tomorrow. Okay, I couldn't get around to doing it mm, recently. Well, in the last week. So, what are the topics that I have not covered yet? One is time series analysis, and another one called ensemble learning. Both are fairly commonsensical. Time series involves a little bit of nuance. So, but anyway, I will record the lectures for them and share them in the portal in today's session. Okay, tomorrow I will do this and then add it to record the videos and add the videos to today's sessions in the portal. But anyway, so today what we are going. Yes, Suvair Bajaj, please go ahead.
So, quick question before you jump in, because you spoke about series and ensemble. I know you haven't done the lecture, but the case study that I picked for the project includes both of these. It's okay for me to have done my own
Yeah,
research
yeah,
and
yeah.
written the report, right? Okay,
Yes, please go ahead.
got it, got it. Thank you.
Nothing wrong in it. Yes, please. Great. So let's jump on to today's topic. It's a very interesting topic. It's one of those very uh, quirky ideas. It's again, in my opinion, this is not any kind of machine learning per se, but except that uh, it's very useful. It's very useful, and uh, at least to me, it's very interesting. So, what is this? It's called association rules mining. This comes under the broad category of unsupervised learning because we do not have any target variable. Okay, we do not have any target variable. Therefore, this comes under unsupervised learning. What is it that we are going to learn? That is, what is that the machine is going to learn under this scheme is they are going to learn rules. Okay, the algorithm is going to learn the rules of whatever rules are there in the data. So, what is it that we mean by when we say association rules mining? Okay, and we start with, again, as always, we start with examples. So, here's an example from market basket analysis, but of course, you can do it for any kind of data. All you want to do is data that is a structured data. Folks, give me just a minute. There's something I need to take care of. Just a minute. 1 minute, please. So, what we are going to talk about is using an example from market basket analysis, but of course, this can be applied to any structured data. Okay, so we will see some examples of this. So, here is an example we start with. So which products tend to go together in a cart is a very common question that retailers would be interested in answering. Why? Because if you know that a particular item is in a cart and other item which usually goes in that cart, with the other item that's already in there, then you could make a recommendation. Okay, so that's very important aspect. That's one of the reasons why this market basket analysis came into So let's take a look at an example. And of course, this example has been, this is a contrived example, of course, but you will see, you will hear people say this from, when professors introduce this, they would say that they had done this work, consulted for a retailer, and this is what they found, and this is what they suggested, so on and so forth. So, but this is actually a contrived example. This has been around for about, this particular statement has been around for about 40 years or more now. Okay. So what is it? It was found that men between 30 and 40 years of age, shopping between 5 p.m. and 7 p.m. on Fridays, who bought milk also purchased beer. Okay, so this is something that some people, a retailer has found by doing some analysis of his or her data. Okay, that retailer's data, looking at all the customers, this is what the retailer has figured out. So what is the big deal of it? So now, when a man aged between 30 to 40 years of age comes to the store between 5 and 7 p.m. and this person is going to purchase milk, you also know that this person is going to purchase beer. So if you put milk and beer on the diametrically opposite sides of the store, then when this person walks from milk to beer, you could have all other products and tempt this person to purchase more than what he was initially planning to, right? So that's the idea. So now, so the decisions could be made, interesting business decisions could be made based upon based upon your rule, the rules that you have figured, right? Now, if we look in this particular statement, okay, it does not tell you that all men, that is men aged between 30 and 40 years, shopping on Fridays between 5 p.m. and 7 p.m. When they bought beer, they also bought milk. That's not the statement. The statement is who bought milk also bought beer, right? So it's a one-way statement. It is not reflective. Okay? You cannot reverse the direction and say that's also true. That's not possible in this case, right? So this is the rule that this retailer has generated. How the retailer generated, we will see it towards a little bit later, maybe half an hour from now. We will take a look at this. But this is the rule that the retailer has generated. Let's now understand this rule. Okay, so I'm going to write it in this fashion. Okay, the essence of this statement is if milk, then beer. Right? That's the essence of the statement. If milk, then beer. But the essence, it's not full. It's not completely true, right? Because if it were women, then the statement is not true. So you see, we need to have something like if men and milk, then beer. Okay, if men bought milk, they also bought beer. But this is also not the case. This is also not fully true. Because if the men were shopping on Wednesdays and if they bought milk, it's not necessarily that they bought beer also. So therefore, we might have if men aged between 30 and 40 years shopping on Friday and between 5 p.m. and 7 p.m. If somebody, if a man comes into the store on Friday, the man aged between 30 and 40 years of age, and came to the store at 4 o'clock or 3 o'clock, perhaps this person was buying milk for his baby. Okay, so he did not stop to buy beer, right? So all these things are important. Now, if you see, we could always, we are able to split this statement into two parts. One part that contains the if statement, and the other part that contains the then statement. Right? It's a simple if-then condition in any programming algorithmic language we know. Right? If, then. Okay? If something happened, then something else happened. Okay? And this is what we call as a rule. If something, then something else. Okay? That kind of a statement is called a rule. Okay? So this particular statement, you know, there's a lot of these rules we could create. This kind of a statement, now if A, then C. If something, then something else. This particular kind of statement and all the mathematics, now there is mathematics behind this. Okay, that may be surprising, but anyway, there's a mathematics behind this. The field of mathematics is called discrete mathematics, and this kind of statements, okay, where A is called the antecedent, it comes first, antecedent. C comes because of A, so it's C is called a consequent. Okay, A is called the antecedent, C is called the consequent. So an antecedent consequent pair is called a rule. An antecedent consequent pair is called a rule. Okay. So we could, since you know it's an antecedent consequent pair, we can simply write antecedent and consequent. Right? Antecedent, then this right arrow, consequent. Okay. Usually, if you're familiar with math notation or physics notation, this symbol, this double line and an arrow, this symbol is usually called implies, but implies sometimes also means causation. Here we do not necessarily mean causation. It's just something happened first and then something happened later. And there's a strong such pattern available. It's not that because somebody bought beer, somebody bought milk, they bought beer. Buying milk caused buying beer. No, that's not the case. People bought beer and bought milk. People bought milk and bought beer. Right? So that's what the statement is. It's just that it's still a statement of correlation, not a statement of causation. So I don't like to call it implies. I just read this as if A, then C. Okay, so we are going to use this notation. Yes, Sam, please go ahead, ask your question.
Can we say that if A occurs, then C would occur?
Yes, you can say that.
Thank you.
If A occurs, then C occurs. Okay, we cannot say if A implies or causes C. That is a wrong statement. But when A occurs, then C occurs. That's okay. Yes, please go ahead. A couple of people have raised their hands. Please go ahead, ask your questions.
Sir, how is it possible that every time A occurred and B will definitely occur?
I'm not able to hear you properly. Your voice, your audio is chopped. Hello?
Well, like maybe because of network issue. Okay.
No, I can't hear I can't hear. Please type it in the chat window. Or if somebody else, if anyone of you heard him clearly, please restate the question. Okay, I'm going to move on. So if A occurred, then C occurred. That's correct. That we can say. Okay. So as I told you, remember that if A then C does not imply if C then A. No, they are not the same. This is like the conditional probability. You know, you reverse the conditions, they are not the same. Same way it is here. No, it is not. So now, example. Now, for example, if somebody is pregnant, then the person is a woman, but it is not the other way around. Okay. So don't come after me in a sociological sense. Biologically, this is what it is. Okay. Now, how do we represent? What is the data that actually looks like? In reality, the data would not be even like this. It would be like, you know, gender, then age, then maybe a time window. They may have had time window. So morning or forenoon, afternoon, evening, late evening, night, something like that. So that's what they might have had in the raw data. And then the day, it might be just the day here, day of the week. Then usually what would they have is in actual data, we might have items bought, which might be separated by a comma. No, these might be comma separated set. Okay. But then what we can do is we can always convert such data into binary variables, because everything is a categorical variable. Therefore, we can do one hot encoding or one hot plus one encoding, whatever you want, right? So we could write it in a binary statement. Okay. Here, remember that these are binary variables. These are not quantities. Okay. If somebody bought beer, yes, 1. If they bought milk, yes, 1. We are not saying they bought 1 can of beer or 1 liter of beer. We are not saying that. They are just saying yes or no. Did they buy beer or not? That's what binary is, right? So we can, the original raw data can be converted into a binary data like this. And then now we can easily form statements from this. Okay. So our original statement is the fourth one. If it's a male, aged between 30 and 40 and shopping between 5 p.m. and 7 p.m. on a Friday and bought milk, then they also bought beer. Okay, that's what it is. So you could maybe you could also say if whether it's a person, whether the person is a male or a female, doesn't matter. Okay, if they are aged between 30 and 40, and if they shopped on a Friday, any time of the day, and if they bought milk, they bought milk and beer. We do not know whether they bought beer and milk or milk and then beer. We do not know that. Okay. So this statement also doesn't tell you whether male aged between 30 and 40, this table, not the statement, this table also doesn't tell you whether male aged between 30 and 40, shopping between 5 p.m. and 7 p.m. on Friday, who bought milk, also bought beer, or who bought beer, also bought milk. That we cannot state that from this particular data set. Okay? That information we have to extract. It's not clear from the data. Okay? Original data is something much raw, and then we converted this into something like this, into a binary. And even this does not tell us how, which rule, okay? Whether milk then beer or if beer then milk, which is true. We do not know, right? So we need to do something to extract that information. How do we do that? Okay. So one thing should be clear. If we want to extract rules like if milk, then beer, or if beer, then milk, one thing should be clear is they should be co-occurring. Okay. The third and the first one, no, they are not the statements that are going to those are not the data sets, those are not the data that fall into if milk then beer or if beer then milk. Okay, only the second and the fourth fall into those two statements, right? So they have to be co-occurring. If A then C means A and C, both of them occurred. That's very important, right? So, okay, I see something in the chat window. I think it must be Prince Dubey. Let me check. Should be what? Co-occurring. The antecedent and the consequent. Okay. For example, if milk, then beer. Both milk and beer should co-occur. Co-occur means it should be there in the same basket. Right? A person bought both milk and beer, or in a tabular column, in such a binary representation, both of them should have 1. Right? That's what I mean by co-occurring. Okay? So let's think about a retail store, a large retail store. You have thousands of items. Okay, thousands of items. You also have other details. You have details about the customers. You have details about the suppliers. You have details about the calendar, time, whatever. Right? So now, if you are going to look at, whether you want to understand why sales are weak on Tuesday, or why some particular item gets sold on the 21st of between the 20th and 25th of the month, much higher than any other days of the month. Okay, if you want to answer such questions, then these dates should have 1 when we put them in binary, and as well as those items, they also should have 1 for a lot of people in the data set. Right? So what we want to see is, we want to see which combinations of these variables occur, which combinations. When I say combinations, those variables which have a value 1, that is the present. 0 means they are not present. The customer did not buy. Right? So which variables occur together, which combinations occur for a large number of customers, right? Sudhir, please go ahead.
So you said which combinations, but I'm also conscious of the fact that the purchase cycle is sequential, right? You're saying if he is purchasing milk, then he is likely to purchase beer. You're not saying if he is he's likely to purchase both. That's not what you're saying. So that means there is a sequence of events saying that if he buys milk, then he's likely to buy beer. It's not the other way around, or it's not ambiguous that he may buy one or the other first. How do they determine this sequence?
25 minutes, 30 minutes from now.
Got it. Okay. And second question is, in the binary table that you had on the previous slide, there was one instance in which Friday milk beer all had 111, but male had 0. It's the second to last one, ID 3. Sorry. ID 2. So assuming that this is a female who's also followed the same pattern?
Yes, female also follow the same pattern in the sense, it's for female, it doesn't matter when they shopped.
Right.
What time of the day they shopped. As long as they shopped on a Friday, if they had milk, they also had beer. Or if they had beer, they also had milk in their basket.
So does that mean that there is a possibility to determine a rule which may not be mutually exclusive to the same rule that you're setting for males?
We are going to look at all these things.
Okay, sorry.
So I'm setting up this. I'm good. You are thinking about these things, but we are systematically going to answer each one of those questions.
Got it. Sorry.
Okay, sure. So some definitions for some time from now, some definitions. The number of items in an antecedent is called the length of the antecedent. For example, in this example, okay, in this last one, for example, we had if men, age, time, day, and milk. There are 5 items in the antecedent. Therefore, the length of the antecedent for this particular rule is 5. Okay. So number of items in the antecedent is called the length of the antecedent. This one is very important. Item set is another important thing. The set of items. That's all. We say item set. No? The meaning is set of items. Okay. So instead of saying it's set of items, we just created a new single word called item set. Okay. It can be antecedent, it can be consequent, all put together, anything. Item set means set of items. So we will be using this term a lot. Okay. Okay. So length of antecedent is one thing. Okay. Usually stated, the number of antecedents is called the length of antecedent here. Okay. Yeah, that's fine. Now, we also have, let's look at the item set itself. Okay. If there is only one item in an item set, there is no rule. If milk, then what? Nothing. So one item sets, with them we cannot form rules. But with two item sets, if we have milk and beer, then we can form two rules. If milk then beer, or if beer then milk. Two rules we can form potentially, right? If A then B, or if B then A, if there are two item sets. So one of them can be an antecedent, the other one can be consequent. Okay. If there are three items in an item set, then C we can have very many actually. If A then B, that's possible. If A then C, possible. If B then C, possible. And the reverse of each one of them. If B then A, if C then A, if C then B, that's totally 6. Then we could also have this. If A and B, then C. If A and C, then B. If B and C, then A. These three are possible. Likewise, the reverse. If A, then B and C. If B, then A and C. If C, then A and B. All these are also possible. Okay. So the moment we have three item sets, the number of possible rules jumps to 12. Okay. Now, if you think about 4 items, 4 items item set, you could see it's going to jump quite a bit. AB, AC, AD, BC, BD, CD. So that's what? 3, 4, 5, 6 totally, right? 6. Reverse that, 12. Then A, BC, A, BD, A, CD, all these different combinations. Okay. So as the number of items in the item set increases, the number of possible rules also increases, not linearly, but geometrically. Okay. So it goes like this. 3 power d minus 2 power d plus 1 plus 1. Don't ask me how you get this. No, it's a very tricky combinatorial mathematics. That's what the entire, these are the kinds of calculations you do when you learn discrete mathematics. Okay. So, but anyway, so this is the number of rules possible. This is the number of rules possible. 3 power d minus 2 power d plus 1 plus 1. So let's say we have 10 items. Okay. 3 power 10. So 3, 9, 27, 81. Then 81 times 3, 243. I can do mental math after. 243 times 243. Okay, that many numbers. Okay. So that comes to about nearly 62,000 or something like that. Okay. Minus 2 power d plus 1, 2 power 11. 2 power 10 is 1024. That times 2. So 20. 48. So the 62, 63,000 something minus 2,048 plus 1, that many rules. So you see, as the number of items that increases, this thing increases drastically, right? Or 57, not even 62, 57. Okay. So this is how when the number of possible rules. Now think about a real retail store. They don't have 10 items, they have 10,000 items. Okay. This is going to blow up on your face. Okay. This is going to blow up on your face. It's going to be huge. In fact, what we have to do is we cannot do this calculation like 3 power 10,000. We might not be even able to calculate. We might have to go to logarithms to do these calculations, do some approximations. Okay. So, so that's how it's going to be worked out. Well, anyway, now, if that is the case, if it is milk and beer, somehow it is okay to figure out whether it is milk or beer by looking at whether milk is antecedent or beer is antecedent by looking at the data. Even if it is 3 item set, we have about 12 of them. Maybe we can look at the data and figure out which rules are valid in the data set. But when you have 10,000 items, this is going to be really ridiculous. Okay. Forget it. Even if there are only 2 or 3 items, how are we going to figure which rules are valid, which rules are not valid in the data? The data drives that, right? Does the data give us enough evidence that A then C, or if C then A? It should somehow tell us. How does it tell us? Okay. So let's take a look at let's take a look at the question. Let's start with a simple example here. Okay, and we'll see how we arrive at that algorithm. Okay. Now, simple data, 13 people. Okay, we have the age category, the income category, age category young, old, middle, income category low, medium, high, family size 1, 2, 3, 4, CC average, credit card spending on an average, monthly average, low, medium, high. Again, this has been categorized. And we want to see whether they have taken a loan, which is this one, or not. Whether they have taken a loan, let's say housing loan, okay, or not. That's what it is. So we want to figure out rules. This is the data. There is no target variable here, right? But we can say, if we can figure out something like if family size is 3 or more and CC average is low, then this person has taken a loan. If you can come up with such rule, that will be useful, right? CC average stands for credit card average spending. Okay. Now, so how do we figure out the rules? Let's start with a simple example. Let's choose an antecedent and the consequent. Okay. So let the antecedent be income is medium. Income variable medium. Income is medium is the antecedent I'm going to look at. Where is income? Income is here. Income is medium. 1, 2, 3, 4, 5 people. Okay. Out of 13, 5 people have medium income. Okay. And let's say the consequent is loan is 1. Loan value is 1. Let's say. How many are there? Loan value 1, 2, 3, 4, 5, 6. 6 people out of 13 have taken loan. Right? There are 2 possibilities. There is only one possibility because we have chosen antecedent to be income is medium, consequent to be loan is 1. So we are essentially we have the rule. We are looking for the rule. If income is equal to medium, then loan is equal to 1. Okay. So if this rule should be possible, there should be a strong evidence for this rule in the data. Okay, what does it mean? That is, income is equal to medium and loan is equal to 1 should occur quite often. Quite often than income is equal to medium, more often than income is equal to medium, then loan is equal to 0. Right? Something like that. Okay. So what we are going to do is we are going to define a quantity called support for the rule. Support for the rule. Let me make it this. Support for the rule. Support for the rule, it looks like an English statement, but support is a very specific mathematical term. What is a mathematical term? It's nothing. It's just that it is a proportion of data that contains both the antecedent and the consequent. What is the antecedent? Income is medium, loan is 1. 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 How many of the, what proportion of the total data has both of these? So if you say 4 out of 13, okay, 4 out of 13, that is nothing but the probability, right? So frequency is probability. So probability that both A and C, probability of A and C, both of them. This is called the support. Support for the rule. In our case, this happens to be 4 out of 13. Right? Okay. So this is clear. That's support. Support for the rule. Is that sufficient? No, that's not sufficient. Why? Because what if there are lots of mediums or there are lots of loans and only a small proportion of them have this combination? Right? Then this would be a meaningless rule. So, very poor. Let me fix this animation. I'm sorry about this. Confidence. Okay, the proportion. So, data containing. Okay. Shapes. Okay, yeah, this is what we had. This is the rule. Income is medium and the loan is also 1. There are 4 out of 13. Okay, so this is the rule that we have. Let's see how confident we are. Okay, so we should be very confident about this. What does it mean, confidence? Okay, the proportion of data containing the antecedent that also contains the consequent. Okay, what does it mean? That is, given the antecedent, the consequent is also there. It's not the other way. Given the consequent, the antecedent. It's not the other way. Given the antecedent, then consequent. So this answers your question about the directionality. Okay, what is it? This is exactly our conditional probability. This is a conditional probability, right? Oh yeah, here. These are the 5 that are there already. That are there with the antecedent in the data. Then the antecedent data. Now, given these antecedents, among these, how many also contain the consequent? Among these 5, 4 of them contain the consequent. Okay. Therefore, we have a very strong confidence on this rule. Okay. 80% confidence, because of all the data that contain the antecedent, 80% of them also have the consequent. Okay, somebody had typed something in the chat. It's not visible to me, so I'm going to take a look at it a little bit later. Okay. Clear up to this? Now, some caveat. Okay, some things to be very clear about. Okay. Support is a joint probability. That is both of them occurring together. Therefore, whether you say if A then C or if C then A, support will be the same. Okay. It just tells you what proportion of the data contains both the antecedent and the consequent. That's what support says. Whereas confidence is not that. Confidence specifically tells you if A then C. Probability of C given A. That's different from probability of A given C. Right? That is, the confidence of income is equal to medium, then loan is equal to 1. That's 4 out of 5. Whereas if you turn the other way around, if loan is equal to 1, which is 6, okay, then income is equal to medium, which is 4. That's 4 out of 6. Obviously, these are not the same, right? It's not the same. So because confidence is a conditional probability, while support can be reversed, confidence cannot be. It has to retain that order. Okay, so that's one important thing we need to remember. Okay, let me go back and see whether you can still see the why it is not showing up. Okay, let me check whether something is wrong. Okay, my chat window is not showing up. I'm not going to be bothered by it. We'll talk about this a bit later. Okay, next. Okay, let's think about a real data where the retailer has thousands of products. Okay, and if you are looking at combinations like if milk, then beer, no, that's going to be, you have a million customers, only a few hundred may be having that combination, right? Maybe every combination you might think, if milk and coffee, then beer, or if milk, then coffee, if milk, coffee, then sugar, if sugar, coffee, then milk. Or you think of any combinations you can think of. Each one of them is going to have a very small support in real retail data, right? So what we need to have is, we need to have that for us to consider any rule, the support for that rule has to be beyond a certain value. Okay, this is the first step in extracting rules. The support for the rule has to be beyond a certain number, beyond a threshold. Let's call it min sup, standing for minimum support, min sup. Okay. Likewise, we can set up a confidence also, the threshold for the confidence. Let's call it min conf. Okay. So only rules that have support greater than min sup and confidence greater than min conf, we will consider. So what are the general guidelines? General guidelines is usually min sub is set about 5% if the data set is small. 10% if the data set is very small. No, you only have about 1,000 records and a few variables. Then you can have min sub guidelines. Then you have min sub to be even 10%. But in the real data, even 1% could be enough, or even that could be large. You might want to set the support min sub to be 0.1% or 0.01%, something like that. Okay. So usually this support is set as a small number because you're looking at the entire data set. In the entire data set, what proportion has this combination of both the antecedent and the consequent? Okay, that's this support. On the other hand, confidence is when you have the antecedent. Okay, I have the antecedent, and if the rule has to be strong, the consequent should be present in many of those. So min conf is set at 50% usually. Okay. Now, here is another definition. An item set having some item set. Remember item set, it is not the rule, item set. AC or AB. Rule can be if A then B or if B then A. Both of them are possible. Just we are looking at the item set. If the item set has a min sub, has a support greater than min sub, greater than or equal to min sub, then that item set is called a frequent item set. Okay. So we are going to use this term frequent item set. What does it mean? The support for that item set is greater than or equal to the min sub. Okay, min sub. Okay, so up to that, well and good. Okay. So what do we have? We have support. We have support tells us what proportion of the data has both the antecedent and the consequent, and if this proportion is greater than the min sub value, then we call this the frequent item set. When you look at the frequent item set, we look at the confidence. The confidence is greater than 50%, then we say, okay, this is workable. But that's not enough. That's not enough. We have to have another very important quantity called lift. What is a lift? Lift is confidence divided by the support for the consequent. Support for the consequent alone. In our case, the consequent is lone is equal to 1. What is the support for the consequent? It is 6 out of 13. Okay. See, if the confidence may be high, okay, if confidence may be high, okay, that is 4 out of 6. Okay, or confidence can be some number. 4 out of 6 could be. Okay, but what if support for C, okay, is very high or very low? 80% of the data has C. What would happen in that case? Okay. This is also 80%. This is also 80%. Then what happens? Or the data, the C consequent occurs only in 20% of the data. Or consequent occurs, let's say, in 95% of the data. So what am I coming to about? I'm looking at these. Okay, I'm going to let's come to this calculations a bit later. Okay. If the support of C, let's say, support of C is small. Okay, that is only 20%. Support of C is only 0.2. Whereas confidence, in our case, let's say is 0.8, 80%, correct? 4 out of 6, not 80%. 4 out of 6 is 2/3, 0.66. If that is the case, then what happens? The lift is greater than 1. What does it mean? Okay, the consequent occurs only for small proportion of the data, but whenever the consequent occurs, okay, the rule seems to have a strong value. That means the consequent lifts the support for the rule. The consequent raises the support for the rule. Okay. The probability of the consequent given the antecedent is greater than the probability of the consequent alone. So when the antecedent is present, you have consequent also. That probability is much higher than just the probability of the consequent. That means the rule has a strong support. Okay, the antecedent is to lift the confidence of the consequent. Okay? The strength of the rule is high. We say the association is positive. It lifts up the confidence, right? So we always calculate and see whether the lift is greater than 1 or not. What if lift is less? Okay, Suvir, please go ahead and ask your question.
Sir, can you tell us what is the definition of lift?
This is the definition of lift. Let us say, okay, out of this, let's look at this, okay? Out of these 13 items, only 6 of them contain the consequent. Okay, 6 over 13, which is a little less than 0.5. The support for consequent is less than 0.5. But if you look at the confidence for the rule, if A then C, then 67% of the time when A occurs, C also occurs.
Yeah.
Right? That means that this ratio tells us that there's a very high, whenever C occurs, there's a high chance for confidence to occur, the rule to occur.
So does it validate the rule?
It kinds of gives a large support to the rule.
Got it.
It increases the support for the rule.
Okay.
Okay. Whereas, let's say, if you had few more mediums here, let us say, okay, then the confidence of the rule would have been smaller. Right? Support for the rule is 6 out of 13. The confidence for the rule, let us say there are 5 of them here are medium. Okay, so totally 9. Okay, so 4 out of 9. So 4 out of 9 divided by 6 out of 13. Okay, it's a little bit close to 1, or maybe less than 1. Can somebody quickly calculate it? 4 over 9 divided by 6 over 13. All these are okay. So 4 by 6, that's 2 by 3. 2 by 3 times 13 by 9. Okay, so 2 by 3. 2 30s are 26 divided by 3 is 27. That's a little bit less than 1. Therefore, the confidence we have on the rule from the information that C is present is actually reduced. Right? Yes, Sri Young, please go ahead.
Yeah, in terms of interpretation, can we say, therefore, that if it is less than 1, even though I have confidence that A can cause C, it is not significant?
No, we are going to say the other way. Actually, That's also significant. Why? Because we know that, okay, if A occurs, okay, then C, it has a low lift, right? It's called a negative association. Okay, we are pretty sure if it is less than 1, then we say the support for the rule goes down. We are very sure for that. We are very sure of that. Okay, so this rule is also important. It is like correlation, like minus correlation means they move the opposite direction. If one increases, the other decreases. That's what lift less than 1 is like. Lift is equal to 1. It's like positive correlation. If one increases, the other also increases. If one decreases, the other also decreases. Right? It's like that. The most problematic thing is when lift is equal to 1. We cannot say whether a correlation exists, whether the presence of C actually tells us anything about the rule. Okay? We do not have any information. Okay? So these kinds of rules where the lift is equal to 1, those rules are weak rules. So we don't have to consider them. Okay? We can disregard those rules. Now, let's take a step back and think about this. We are all dealing with computers and we are dealing with probabilities, numbers, one divided by the other. We are very rarely we will get an exact value of 1. We may get 0.95, 0.97, 0.93, 1.03, 1.07. We might approximate them to be equal to 1. Therefore, what we usually do is we will set a range for the lift is equal to 1. Okay? That is, if the lift lies between 0.9 and 1.1, then we would say the strength of the rule is weak. Okay? We will not consider those relationships. Other relationships, yes, we will consider them. Okay? This is how we will see out of all those possible rules, calculating these probabilities and these things are very easy. It's just proportions. Right? These are very easy. Therefore, we will use these values, namely the lift, the confidence, and the support, the confidence, and the lift to determine whether a rule is important or not. So how do we do that? Determine the support for all k item sets. If you have k items, okay, for all the k item sets, from k is equal to 1 to all the way to d minus 1, or actually d, when all members all are present. Okay, so you create. This shouldn't be k is equal to 2. K is equal to 2 d. Okay. No, this also we need, because this support we need for calculating the lift. Okay. Now identify item sets that have support greater than or equal to min sub. You have set up the threshold, so you can quickly rule out quite a few of these item sets. So you identify the frequent item sets. Now, among the frequent item sets, for each one of those rules in the frequent item sets, determine the confidence, and only extract those rules which have confidence greater than min conf. You got min conf. Now, from these rules, now what you want to do is you identify only those rules which are lift not equal to 1. that is lift less than 0.9 or lift greater than 1.1, for example. So systematically, you are reducing this set of rules that you can work with. The first step is very easy. It's just proportions for each of these item sets. That's easy, support. Right? That's easy. Now, from those frequent item sets, you create different rules, and for each rule, find the confidence. Now, that's again probability, very easy to calculate. Then you have support and probability. You already calculate, do the division, you get the lift. So the calculations become fairly easy. In terms of the number of computations, it's very easy. Right? And now once you have identified the rules, you can use them for further action. Okay? This is how this is the background theory of association rules mining. Okay. So what we are going to do is we will see in action. I'll take an example and show you two algorithms that help us in identifying these rules. Okay. So we are going to look at this algorithm called a priori algorithm. I'm going to use 10 baskets or data set of 10 people, 10 customers who have bought these items. Okay. Using these items, we will see how these things actually play out. Okay. So we'll come to that in a short while. We'll take a short break. The time now is 7:36. How about let's take a break. 7:45, 7:46, 7:47 on my watch here. We will meet once again. In 7:45 or 7:46, we will meet once again, and we will consider these two algorithms. One algorithm is called a priori algorithm, and the second algorithm is called frequency pattern growth, FP tree growth, frequency pattern tree growth. We are going to do some growth of trees, okay? And we will use these two algorithms to see how rules can be extracted. Okay? So we'll take a short break. Okay, let's meet at 7:45. That's all. No, 7:50. 7:50. We'll meet at 7:50. Let's take a 12 minutes break. We'll meet at 7:50 on my watch here. table. So for each person, we can write what are the items that they have purchased. This way, we can easily calculate. Why do we give it this way? This way, it is easy to calculate the support. Just sum of them. Sum that will give the number of people who bought bread divided by 10. That will give you the support for each one, right? Okay, now we'll start with support. Support for one item sets for each one of them, right? So let's set minimum support to be 0.2. And since this is a very small set, I have a large threshold for the means up. No, so this is what I find: 0.7, 0.3, 0.9, 0.3, 0.5. So every item here has a support greater than the mean support. So each one of these is a frequent item set. One item sets, each one of these. Now let's go one step above, look at all two item sets. Okay, two item sets. So what could they be? Bread, lettuce, bread, cheese, bread, milk, bread, coffee. Lettuce, cheese, lettuce, milk, lettuce, coffee, cheese, milk, cheese, coffee, and milk, coffee. These are the possible two item sets, right? Bread, lettuce, bread, cheese, bread, milk, bread, coffee, lettuce, cheese, lettuce, milk, lettuce, coffee, cheese, milk, cheese, coffee, and then milk and coffee. 10, right? So let's do this. Calculate the support for each one of them. I'm just giving a demo here, so I'm going to show only a few of them. Okay. So bread, lettuce, bread, cheese, bread, milk, and bread, coffee. So if you look in this, bread and lettuce, there is one, and nothing else. There is 1 out of 10. So it has a support of 0.1. Okay. And bread and cheese, as you can see, 1, 2, 3, 4, 5, 6. 6 out of 10. So on and so forth. Okay. Now let us. Okay. It's very poor animation. So let me do one thing. So now let's look at these combinations. Yes.
Coffee is 0.6, I believe.
Coffee is 0.6 in our thing. 1, 2, 3, 4, 5, 6. Yeah, sorry about that. So bread and milk, let's check that. Bread and milk, 1, 2. That's correct. Bread and coffee, 1, 2, 3, 4. Okay, these are all correct. Now let's compare one thing. Bread and lettuce together 0.1. Bread alone 0.7, lettuce alone 0.3. Okay. Likewise, bread and cheese. Bread alone is 0.7, cheese is 0.9, together 0.6. Bread and milk. Bread 0.7, milk 0.3, together 0.2. Bread and coffee. 0.7 bread, 0.6 coffee, 0.4 together. You see, each one of these two item sets, they have support less than the individual items, right? Less than the individual items. This is a key understanding. Okay, all these combinations have support greater than the min sub. well and good. Okay, let's look at some other examples, some more examples. Lettuce and milk, both of them have 0.3, 0.3 individually, but together how much? 1, 2, only 2, so 0.2. Again, you see lettuce and milk 0.2 less than the support for individual ones. Cheese and coffee 0.5. Let us check. 1, 2, 3, 4, 5, 6 actually cheese and coffee. I have written 5 here. Cheese and coffee, milk and coffee only 1. Okay, so you see every time you see if you have 2 item sets, their support is, look at cheese and coffee. Cheese and coffee support is 0.6, for cheese it's 0.9, for coffee it's 0.6. So support of this is either equal to or less than the support of the individual items, right? When you look at 3 item sets, let's for example take bread, milk and coffee. Milk and coffee itself has only 0.1. So if you add one more to it, its support can be either 0.1 or less, right? It's 0.1 or less. So you see it is now it becomes fairly easy to prune item sets. Any rule with bread and lettuce is going to be unimportant. Why? Because anything that contains bread and lettuce will have a support less than 0.2, less than our min sub. So the moment you know this, every other combination, for example, bread, lettuce, cheese, bread, lettuce, milk, bread, lettuce, coffee, bread, lettuce, cheese, milk, bread, lettuce, cheese, coffee, bread, lettuce, milk, coffee, all these things will be not important because they have support less than the min sub. Same thing with milk and coffee. Any combinations here. So any item set that contains milk and coffee, you can discard. Likewise, any item set, of course, here milk and coffee, so this is already discarded, right? So this is called a priori. Already a priori, beforehand, we decide. Beforehand, we decide what are the useful item sets. How? You look at the previous ones and then you can say, the moment I have these 2 item sets, with some of them having support less than min sub, every superset of these will also be unimportant. Okay.
Can you
So,
explain again?
what is-
I got lost.
Say it again.
Can you just explain the last section again? I was lost for a moment.
Yes.
Like the a priori, like what is important and which is not important.
So the moment, so what we are going to think of it similar to the step up regression. Okay, stepwise regression upward. You're starting with 1 item sets. You calculate the support. You find which of these item sets are having support less than min sub. Okay. Now, what if there are any? In our example, there is none. But if there is any, then every item set that has that particular item set, every other super item set, say for example, in this case, we have bread and lettuce. Okay. If you consider any 3 item sets, 4 item sets, or 5 item sets that contain bread and lettuce, their support will be 0.1 or less. Okay, 0.1 or less. Okay, why? Because bread and lettuce already has only 0.1. So anything bigger you build with this will have a support less than this. Therefore, we do not even have to consider item sets that contain bread and lettuce. Likewise, that contain milk and coffee. Now, of course, I have not checked lettuce and cheese, lettuce and milk, cheese and milk, all these other things I have not checked. But you can go ahead and check those. All those item sets that have a support less than the min sub, any superset built with them will also have support less than min sub. So we don't have to look at those bigger item sets made with these things, bread and lettuce or milk and coffee. Yes, Suvir Bajaj, go ahead, please.
So, what is the relationship between discrete mathematics and common logic on this slide, on the previous slide? Because, if I have to just apply common logic over here, someone buying bread and someone buying cheese together, logic would say that's a great combination. But,
Yeah.
having said that, the numbers don't necessarily validate. I assume it's because we're looking at it sequentially, etc., so on and so forth. So, how does one navigate this conundrum?
Well, this is one simple example. It's not how is discrete mathematics is different from common logic. I have no basis to comment on that because I don't claim to understand full of discrete mathematics or common logic. So I would refrain from answering that question. But I have heard mathematicians say mathematics itself is just logic. Okay, so except that the logic is not so common. That's the only thing. So in that sense, yes, many a time I feel that the entire data science beyond regression is just application of common sense, okay, with a little bit mathematical push. That's all. That's my take. But you are right. You can think of it. It's just common sense. Yes, very true. We just are codifying it. That's all. Like I told you, when I learned all these things, my professor did not tell me, or even there was nothing written about training set and test set and how you have to split data into train set and test set. It was considered common sense. Okay, except that starting graduate students do not have it. They fail once or twice, and then the sense they get the sense of thing, and it becomes common sense. No? So, in a sense, you are right. So what is this a priori algorithm? A priori algorithm says if an item set AB is frequent, then any superset of AB is only as frequent as AB or less. Okay. Here frequent means I'm talking about the support. Okay. Any superset of AB will have a support less than or equal to the support of AB. Okay. That's what it means. So in terms of mathematics, we can write this okay. So insert OLE objects, funnel object. So what we can say is identify support of a superset of A comma B, yes, less than or equal to of, okay, I should say this, let me write fully. So all you are trying to say is, if we have, if we know the support of A and B, the support for every superset of A and B will be less than or equal to the support of A and B. Okay. Likewise, we will say support of it's not superset. It should be what you call super infraset of A, B, comma, C will be greater than or equal to subset of A. This is the
Why do you switch
Infraset.
subset to why do you switch that from sub to infra?
Yes. Yes.
Oh, yeah, okay, because it's
Smaller set. I mean by infra, I mean smaller set. Okay.
same as the subset.
Smaller subset. So that's what we mean. The support for superset is always less than or equal to the support of that set. The support of a smaller subset is always greater than or equal to the support of the current set. Okay, so these are the driving principles of a priori algorithm. So what does it mean? Okay, with this now I can remove these 2 points that I've already given. Now I can make this bigger. So what does it mean? So we start from one item sets. For example, in our case, no, like what we had, one item sets, all of them were frequent item sets. They had a support greater than our min sub of 0.2, right? Now we formed all the 2 item sets. Among those, few of those are not frequent. Okay, they are not frequent. AB, BE, and DE, they are not frequent. Therefore, every superset of this will also be infrequent. For example, ABC, ABD, ABE, they are infrequent. ABCD, ABCE, ABDE, okay, ABCD, ABDE, they will also be infrequent. Likewise, ABCE and ABDE, they will all be infrequent. So all these are infrequent. Likewise, you could see this. Okay. So if you look in the third 3 item sets, you can immediately say anything that contains BE, like here or here, BE, here BE, they will be infrequent. Anything that contains DE, for example, DE here and DE here, they are infrequent. And here, ADE. Okay. So they are all infrequent. So this way, we don't have to form all these item sets. We don't have to look at all these rules, etc. So instead of looking at how many, 5 plus 5, 10, 10 plus 1, 2, here is 10, and here 1, 2, 3, here is 10. 10 plus 10, 20, 20 plus 10, 30. Out of the 30 item sets that we should, within quotes, try, it is enough if we try 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Only 50%. Exactly in this example, only 50% of the item sets that are possible, we will actually need to test. Okay. So you build this step by step, and then you can now form rules. So this way, okay, start with k is equal to 1, find one item sets that are frequent. Frequent means greater than min sub. Support is greater than min sub. Find the supersets of these frequent item sets. Find the plus 1 k items, plus 1 k, that is whatever k we had, add one more, keep doing it. Okay, at every stage you see which are the ones that have support greater than min sub. You have to do it only from the frequent addresses in the previous step. Okay, some of those could become infrequent, right? Okay, I'm not able to see this comment. I'll wait for some time. Keep repeating the process until no frequent item set is found. Then for each of those 15, in our example, we identified 15 item sets. For each one of them, 5 of them, no need because they are one item sets, so gone. So for the 10 item sets, for the 10 of the remaining item sets, you do for this 10. Here is 7, here is 3. For these 10 item sets, you create the rules, all possible rules. If A, then C. If C, then A. If A, then D. If D, then A. If A, then E. If E, then A. If AC, then D. If A, then CD. If C, then AD. All those kind of things. Okay. So form all those rules and identify which rules have confidence greater than min conf. Identify only those. So now you have only few rules that have confidence greater than min conf. Take those, and among those find which ones have lift different from one. Okay, and use only those. Use only those. Those are the ones that are important. Make actions beyond. Make actions based upon them. Okay. So let me see. Somebody had.
So can you go back to the previous slide for just a second? Thank you.
The problem with this is, for demo purposes, I just took 5 item sets. It's easy to conceptually get what is happening, but in reality, this could actually grow quite big. Think about a real retail store. Okay, 5,000 items. Let us say 5,000 C2. Okay, so that itself is huge. 5,000 times 4,999 divided by 2. 4,999 times 2,500. That many 2 item sets we will have to create. Okay, so this could become very large because the number of the combinations, again, they are geometric, and in each combination the number of rules, they are geometric. Okay, so the number of rules grows geometrically with the number of items. Okay, therefore computational complexity is high, the time could be high. Okay, so it could be a very computationally costly. It's very easy to understand algorithm, very intuitive, as the other gentleman said. It's actually common sense algorithm. Okay, but the challenge is it's expensive. It's expensive. Therefore, what people have done is we have looked at another type of algorithm called FP growth, frequency pattern growth. Okay, so we are going to look at frequency patterns, essentially which ones occur together, that kind of thing. We are going to see in a slightly different manner. This algorithm is much more, it's much cheaper than the a priori algorithm, and it's quite fast. So FP growth is the standard go-to algorithm in the industry. Okay, so what do we do in this? Okay, so we have to do a certain type of pre-processing before we do the frequency pattern growth or FP tree growth. What processing? We calculate the support for all one item sets as before. First start with one item sets, calculate the support. Then discard all items that have support below the min sub from each record. From each record, okay, remove these remove the item which is not a frequent item. Remove that from each record. Okay. Then what do you do? Each record you sort the items such that you sort from highest support item to the lowest support item. Okay, for each record. For each record. This is the pre-processing we have to do. So let us look at this. Now the same type of data, I modified the data slightly. Okay, that's a little bit of change, but let's see what I have done here. So this is the binary representation of the same data. Okay, so if we calculate if we let the min sub to be 0.2 and calculate the one item set support, okay, we see bread has 0.7 as before, cheese 0.9, milk 0.3, coffee 0.5. Lettuce also had 0.3 earlier. I have removed lettuce from 2 of them. So in this data set, lettuce has only 0.1. Okay, so we drop lettuce. We drop lettuce. Okay. So where is lettuce? The second one. Second one, we remove lettuce. Okay. So our we drop that, lettuce is gone. Second one. And then what did we do? Each record we arranged in the order of decreasing value of the support. So cheese first, followed by bread, followed by coffee, then milk. Cheese, bread, coffee, milk. Cheese, bread, coffee. Cheese, milk. Cheese, bread, coffee. Every record you arrange in terms of the decreasing value of support. Okay. So this is the pre-processing we do. Now we start building the tree. How do we build the tree? We start with the first record. We start with the first record. Okay. And then say we build the root node. We say cheese. Cheese is the first item. Okay. And next to cheese, we have bread. And next to bread, we have coffee. At the first item, at the first record, this is what we have. 1 cheese, 1 bread, 1 coffee. Okay. Well and good. Then what do? We go to the second item. Okay, ID 2. Root is still cheese, obviously. So now we already had cheese, and now we have 1 more cheese. So cheese becomes 2. We had bread earlier, and now bread also becomes 2. We had coffee earlier. Coffee also becomes 2. We did not have milk earlier. Now milk becomes 1. So we are counting the frequency. We are counting how often every item occurs as we go down the records. As we go down the records. Then third record, we have cheese. Okay, there is no bread. Cheese is 3 times now because there is cheese here. So cheese becomes 3. But bread, milk, and coffee, and milk, they don't change because that's not available in the third ID. But then milk is there after cheese. So this should become 2. No, it doesn't become 2. Why? Because this comes after coffee. But in our third record, milk comes after cheese. Therefore, we have a branch. Cheese and milk. Okay. First branch, second branch. Now go to the fourth one. No, we have cheese 4 times, bread 3 times, coffee 3 times, milk 1 because the fourth one doesn't have milk, and then there is other branch, milk is 1. So this way you keep building. You keep building. Cheese 5. Okay. Now look at this. It doesn't have bread. So this branch remains the same. Bread, coffee, milk. It also doesn't have milk. So this branch also remains the same. So new branch is formed with coffee for the fifth one. Right? So you keep doing it until you exhaust the entire data set. So when when you exhaust the entire data set, when you have gone to
anh đeo trễ lắm luôn á, mà em đeo không có dễ chút nào
excuse
hết.
me. Okay. So once you have gone through the entire data set, we see cheese occurs 9 times. After cheese, bread occurs 6 times. After cheese and bread, coffee occurs 4 times. And after bread, cheese, bread, and coffee, milk occurs only once. So we got this branch. Then we have cheese, bread, milk. Then cheese, milk, cheese, coffee. And there is another new node, bread. Right? The 6th one, bread. Okay. This is what we have. Okay. Now we have built the tree. Now, drawing the tree, it's not big deal. No, it's very easy. Now, all you're doing is counting. So this is fairly fast computation. Okay. Now, what do we do? What we do is start from the pick one item set, any one item set. Okay. So we say milk here. Randomly, we say milk. Okay. Check and see if it is frequent. Okay. Obviously, it will be frequent. Why? Because if it is not frequent, if its support is than the min sub, we have already pruned it. So we don't have to do it, but just check whether it is frequent. Just a double check here. Okay. Now what you do? Create all 2 item sets ending with milk and find their support. What are the things that end with milk? Milk, coffee and milk, bread and milk, cheese and milk. These are the only things from our tree. You see, coffee and milk, bread and milk, cheese and milk. Only 3. So for each one of them, find what is the support. Okay. Bread and milk support is only 1. Cheese and milk support is only 1. So those 2 are infrequent item sets. Okay. Coffee and milk, that's also 1 item set. Sorry, that's also infrequent. So no 2 item sets ending with milk is frequent. Now combine this with a priori. No 3 item sets ending with milk is frequent. No 4 item sets ending with milk. No 5 item sets ending with milk. It's much faster than the a priori itself. Okay. So every item set that ends with milk, we can draw. Okay, we can draw. Okay. Now, what do you do? Go choose another random 1 item set. Okay. So check for that. Repeat the process. In our case, coffee. Let's say I've chosen coffee. So coffee, 2 item sets is bread and coffee. That's possible. Cheese and coffee. Only 2 are possible. Right? Bread and coffee, cheese. Out of these, cheese and coffee has a support of only 0.1. And bread and coffee has a support of 0.4. Therefore, we have 1 frequent 2 item set ending with coffee, bread and coffee. Now you can see whether build 3 item sets with bread and coffee. The only thing possible is cheese, bread and coffee that has a support of 0.4. So you have only 2 item sets now: cheese, bread and coffee, bread and coffee. Only these 2 are the item sets that are meaningful. Okay. Repeat this for every 1 item set. Repeat this idea for every 1 item set. So you can see anything that ends with milk, no, doesn't, it has no thing. Anything that ends with coffee, there are only two item sets, bread and coffee, cheese, bread and coffee. Then you look at bread, only cheese and coffee. Only cheese and coffee. Okay. Anything that ends with cheese, of course, there is nothing. So, in effect, in our entire thing, we have only three item sets: bread and coffee, cheese, bread and coffee, cheese and bread. That's all. See, this is much faster than a priori. Now, for this, go and do the same thing. For each one of them, create the rules from each one of these item sets and identify the confident rules. From those, prune away the ones with lift equal to 1. Okay. So this kind of identifying the frequent item sets is called frequency pattern tree. Okay. We had frequency pattern tree for coffee because it's ending coffee. We can do frequency pattern for milk. We did not have any. Frequency pattern for bread, we have only one. No, likewise, you can do that. Okay. So this is what, okay. So for example, bread and coffee, cheese, bread and coffee, only these rules are possible. If bread, then coffee; if coffee, then bread; if cheese and bread, then coffee; if cheese and coffee, then bread; if bread and coffee, then cheese, blah, blah, blah. Okay. Then you can do cheese and bread. Okay. So that's it. So cheese and bread would be 2 more. So out of all the possible 30 rules, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10 rules like before, right? So we identify these things much faster here than in the previous case. Okay? So this becomes much more useful when the data set is larger than our demonstration here. Okay. So to close, what is it that we have done? In a given data set, we have tried to understand the relationship between different columns, different variables, and we see whether any rules can be extracted about the data, about these variables actually. Okay, and those are done using probability, calculating probability. These are probabilistic statements. These are not deterministic rules. These are probabilistic rules, right? And you use simply probability, which is support, conditional probability, which is confidence, and then it's something like a likelihood ratio, which is called the lift. It's a ratio of probabilities, okay, which is called the lift. Okay, and that's what we do. These things are now, even though the examples we showed are very simple, it's a simplistic actually. The complexity of the calculation of the identifying the rules depends upon the support. Okay, the lower the support, okay, the higher the complexity. Right, the lower the support, the higher the complexity. Okay, especially if the min sup is low, then you probably have lots more item sets that are frequent. Therefore, the complexity increases. Okay, and confidence and lift are post-processing filters, but support is the one that actually drives the complexity of the algorithm, and you have to be tuned to the problem and your expectation, what you are looking at, what you are trying to achieve, okay, to see how to use this algorithm. So with this, I'll stop here for this association rules mining. I will update this. Why add is infrequent. I can see ADE. Oh, AD is infrequent. See ADE in second line is infrequent, but in line 3 it is coming as frequent. Really? Let me go and check. This is Prince Dubey. Let's check that. Shouldn't be AD. AD is frequent. It is not infrequent. Okay. So ADE is infrequent because DE is infrequent. It's the other way around. Okay. So you check this anyway. So with this, I'll stop here. We have actually about 1 hour more. So what we can do is this. Let's take another short break. Okay. Let's come back and we will cover one other topic. Namely, let's try to finish off ensemble learning. It's a very easy idea. I'm going to only introduce you to the concepts of this. Okay, so we'll take a short break. When it's 8:45 on the watch here, I'll come back and we can start learning about ensemble learning. Okay. Okay. try to cover this as quickly and as simply as possible. But of course, it will take another 45 minutes or so. So be patient. But it's a very, very, very interesting idea. Okay, ensemble methods. What are these ensemble methods? Ensemble means collection. Okay, that's all. Ensemble. Now, what do we do in this? So far, what we have done is we have mentioned that come to the optimal model, come to the optimal model, come to the optimal model, right? So how do? We build a lots of models, and then from them select one good model. That's the kind of idea that we were focusing on. Now we are going to do slightly different thing. What are we going to do? We are going to say, okay, don't worry about building. Don't be obsessed with getting one best model, but rather get a lot of models. Okay, get a lot of models. Each one of them may be slightly less than optimal. That's okay. But when you have lots of models and you combine their outputs, when you combine their outcomes, this combined outcome will usually be better than the outcomes of the individual models. Okay, this is the kind of idea that drives this technique called ensemble technique. I'll demonstrate this. Okay, so if you have multiple models, okay, I'll demonstrate this with a simple example. Okay, so okay, these are three we are going to talk about, but before that, let me start with this simple idea. Okay, if there are m independent classifiers, let's look at classification schemes, classification models. Okay, if there are m independent classifiers, okay, what do we mean by independent classifiers? Now we have built this in different models, and we think these are independent of each other. Okay, that is, the performance of one does not depend upon the performance of the others. Okay, if there are independent classifiers, then what does it mean? The errors these models make are uncorrelated. That's what it means, right? The errors, if they're independent, that means the correlation is very poor. What is the correlation between what? The errors is very poor. If they are dependent, then the correlation of errors is high. Okay, let's take a look at this. Okay, two kinds of extremes. One extreme where let's start with the three what we think as independent classifiers. Okay, three classifiers, three models. Classifiers means model. Let's say we have three models. Okay, and let us say these three models are identical. For example, our linear logistic regression model we built for Framingham heart disease study and Varadarajan's blind classification. We got the same results, right? So let's say that kind of model, that the identical models, what would happen? Here is an example. Okay, we have binary classification scheme. How many? We have 9 points. Okay, 9 points. First 5 of them are in class 1. The next 4 are in class 0. First 5 class 1, next 4 class 0. Okay, let us say that we have 3 identical classifiers. What does it mean? Each one gives the same prediction for each one of these data points. Okay, and let us say each one of them has a base error rate of 0.33. Three of these they make errors in. Okay, 3 of these they make errors. Since they make the same errors, the combined error will also be the same. What do you mean by combined? I am saying, how can we combine 3 different models? Voting. No, you give voting. So whichever, if 2 models say one value, that's what I will consider for the ensemble. Okay, it can be either 0 or 1, right? So if you have 3 models, 2 of them have to agree. Definitely, the 2 of them have to agree, right? So, which if 2 say 1, if 2 say class 1, then I will assign class 1 to that particular data point. Okay. If you see, if that is the case, in this case, if we have identical classifiers, 100% correlated, I have the same error rate as the baseline. Same error rate as baseline. Let us say 100% disjoint classifier. That is, the data for which they make errors are different for each one of them. Okay. For example, in this case, okay, the first classifier makes errors in the first 3. The second classifier makes errors in the second 3. The third classifier makes errors in the third 3. If this is the case, they are completely disjoint, 100% disjoint classifiers. Okay. Then if I look at the overall ensemble prediction, then I have 0 error rate. I have 0 error rate. On the one hand, I have the same error rate as baseline, where all models are identical. On the other extreme case, where they are completely different, I have 0 error rate. In reality, if we have 3 models, our 3 models are going to lie somewhere in between these 2. They're going to lie in between these 2, right? Therefore, you expect an error rate that lies between the baseline and 0. Okay, so baseline and 0. For example, in this case, I have some random scheme here, get an error rate of 0.22. Okay, this is better than any of these baseline errors. Correct? So this is the idea. Okay, so the realistic ensembles are going to lie somewhere in between identical classifiers and completely disjoint classifiers. Realistic classifiers are somewhere in between. Therefore, the error rates are also going to be in between these 2 extremes. And this is the idea that drives ensemble models. We can use the same thing for regression also. Sam, please go ahead.
Can you parallel this to like general elections, where you have many voters, and some voters will make mistakes, they will make errors, and some voters may not make so much errors, but you total them up together, it's very powerful. The whole group of voters will vote for the right candidate.
What do you mean by make errors when voters make error? Voters don't make error. They just vote.
Yeah, correct. Some
So-
may vote for the wrong candidate. There are certain will make mistakes.
I don't know whether there is a right or wrong candidate, because whoever gets elected gets elected. Let's think about the other way. Let's say we have exit polls.
Okay.
Okay, so let's say there are 3 different organizations doing the exit polls.
Okay.
Okay, and each one gives predictions. Okay, this candidate will win, in that candidate will win, so on and so forth. So let's say there are 10 or let's say 100 seats for which elections happened.
Yep.
And then these different exit poll organizations, they give some of their predictions. For each seat, they give some prediction.
Mm-hmm.
Okay. Now, if you look at the ensemble is usually going to perform better than any one of these individuals. And that's what the claim we are making. Okay? The accuracy of the ensemble is going to be better than the accuracy of any of those individual exit polls. And that is the fact when you have elections happening. Okay, you will see poll of polls. Many organizations, what they do is, in spite of they conducting their own exit polls, they also collect data from other exit polls, combine all of them, and then give poll of polls verdict.
Right.
Okay, so that's what we are talking about, the poll of polls.
Thank you.
So what are the so this is what majority voting. That's what we are doing. That's the idea for classification. So this ensemble technique, okay, we have three different types of ensembles that are very common. One is called bagging. Bagging stands for bootstrap aggregating. That's what bagging stands for. Then there is something called boosting. Then there is something called random forest. Okay, so once I understand this idea of how ensembles do better than individuals, it's now just learning the techniques. That's all. So let's quickly learn these techniques. Okay, so let's look at. Here is another example. This is an example for again a classification. The example comes from what is called IRIS data set. It's very common data set. The data was collected about 100 years ago on iris petals, iris flowers, their geometry, their shape, and this data has been used to demonstrate a variety of machine learning algorithms. Here is one example. I'm not going to go through it. You just get an idea. So in this example, you would see that ensemble vote classifier. We also have what is called the weights. You could give equal weights to all three, which is what I demonstrated in this particular case. But you could also give different weights for different models. Okay, basically because you might think that one model is slightly better than the other, or you could do some subjective metric like variance, okay, to determine the weights. But here, just a demonstration, we are giving different weights for these three different models for classifying some kind of classification for the iris data. And you see that the individual accuracy, the accuracy of individual models, each one of them is 0.86, 0.82, 0.93 in the training set. Obviously, the ensemble is better than or equal to all the three, 0.93. Okay? And the test accuracy happens to be 0.97, which is fairly, which is actually, this is to me is doubtful. Anytime the test accuracy, this is another thing we did not talk about when we talked about the error versus complexity plot. In the error versus complexity plot, if you go back and see, the training error starts from very high value for under represented, what we call underfit models, and goes to 0 for overfit model. And for the for the test set, it's always underfit, it's high, and then decreases, and then for overfit also it goes high. But you would have noticed that the test set errors are higher than the train set errors. Okay, therefore the test accuracy also I would usually think a little bit less than. Here they are saying validation accuracy, which is okay, but still for the test accuracy, okay, I wouldn't expect this much. That seems still something needs to be done here. But anyway, the idea is here to demonstrate the ensemble method, how it works. The ensemble method works either at least as better as the best of the individual models. Right? That's what we see here. Okay. There is one chat message. Let me see. Okay. Sorry, what does K in that? What does K mean in K is equal to 1? I suppose this is for the previous topic. This is K. Essentially, I'm talking about how many items in the item set. I used the symbol D earlier. I should have stuck with D, but somewhere without realizing I changed it to K. Okay, so D, the length of the item sets. Okay, there is only one item. If K is equal to 1, that means one item set. Consider classifier as a decision tree and ensemble is a collection of decision trees. Hence, if one tree gives an accuracy of 80 and the other gives 70, then the result would be 80 plus 70 by 2. Not necessary, not that. I'm not saying that. I'm not saying that. Okay, I am saying something very different. This is okay. This is okay. Okay, this is what is expected, but what I'm saying is, I will see what I'm saying in a minute. Okay, let's start with bagging, bootstrap aggregating. What is meant by bootstrap? I'll leave it to you to read these things. Bootstrap is essentially sampling the data and creating a new data set of the same size by sampling from the original data by replacement. What does it mean? Let us say original data, we have 10 members, 10 different members. Okay, I'm going to create a new set with 10 different members, 10 members, by sampling, randomly picking one member at a time from this 10, from this original set. Every time I pick, I take a copy of that in my new set. I'm not going to put it here. I'm going to take a copy of that. That means this is called sampling with replacement. Okay, I randomly picked X8. I put it here, but X8 is still there. What does it mean? Again, when I randomly pick, there is a possibility I might pick X8 again. For example, I have picked X8 again. Okay, here is another time X8. Okay, and for example, X2 I have picked twice. Right? So this is called sampling with replacement. Randomly pick one member from the original set, make a copy of that in the new set. Repeat this until the new set is filled. When we do this, then what happens is there is a possibility that some elements, some members of the original set are not present in the new set. This new set I call a bootstrap set, a bootstrap sample. And some elements occur more than once in this bootstrap sample. What does it mean? I am by some random sampling technique, some points lose their importance, some points increase their importance. In this example, X8 increases its importance, but X3, X7, X10 completely lose their importance. Okay, I do a different sample now, different bootstrap sample. I won't get the same again. I'll get a different one. For example, in this case, X6 and X9 become unimportant, completely unimportant because they are not there. But I have X1, and then X1 is present a couple of times. Others are present on one time. Right? So you can do multiple bootstraps like this. And what do? For each one of them, build a model, whichever model you are using. If it's sample, if it's classification, use logistic regression or decision tree or whatever technique you know. If it is regression, use linear regression or decision trees or whatever whatever, you know. Right? Use any one of these techniques, whatever techniques you use those to do the task you want for each one of them. So since the data is different for each one of these bootstrap samples, the model you get for each one of them will be different. The model you get for each one of them will be different. Now let's think about this, the first one, okay? Think about a multi-dimensional space where your data points are vectors pointing in different directions. And by this bootstrapping technique, what you are doing is your few vectors are not looked upon at all. They're not considered at all in the model making experiment. That means you are building a model for a sub-region of this feature space. The region where your missed out vectors are there, that you are not considering. You are considering the remaining space. Right? So that when you build lots of such models, in one model you are looking at this sub-region, in another model you are looking at this sub-region, in another model this sub-region, another model this sub-region, so on and so forth. So what are you doing? You are building models that are optimized for different sub-regions. Of course, they will have overlap. Of course, they all will have, each one will overlap with at least one other. They have, these sub-regions will have overlap. Okay. Now what happens? Instead of having one model fitting one model trying to predict a value for one vector, now you have multiple models predicting the value for the same vector. And therefore, your average, some models are going to overfit, predict a higher value. Some models are going to predict a lower value if it's prediction. And therefore, you will get an average which is much closer to the actual. Likewise, if you have classification, some models are going to misclassify, some models are going to correctly classify. And since these models are optimized for the subregions, more than one model is optimized for the subregion, the accuracy is increased compared to any single model. Okay. This kind of modeling is called bootstrap aggregation. We are bootstrapping and then aggregating. What is aggregating? Combining all of them together. We are bootstrapping and aggregating and aggregating. Okay, aggregating. That's all. It's a very simple idea. So what are we doing? We are doing a sampling in the data. Okay, we are doing a sampling in the data. Okay. So this is called bootstrap. With bootstrap is nothing but sampling with replacement. Okay, so I told you all these different things. That go ahead.
Sir, if a data set is large, okay, what should be the sample size and how many bootstraps should be created before aggregation?
The same size as the data set.
As the data set. And how many such bootstraps should be created so that we ensure that there is no loss of a data element, at least not being picked up once?
Yeah, that's a tricky question. Okay, because if the data set is very large, okay, you might want to do a lot of bootstrap samples. Okay. So now that means the complexity of the problem blows up. For one sample, which is of the same size as the original data, you will use some resources. You are going to use that many resources again and again every time you do the bootstrapping. So the complexity grows linearly.
Got it, sir.
Computational complexity. So you do a kind of a heuristic. For large data set, you do about 1,000 bootstraps. Okay, I remember I read a fantastic paper. It was a paper on what is called amblyopia, cross-die. I told you about my research area.
Yes.
They had about 532 was the sample size. Okay, and they did 1,000 bootstraps to
That's quite a bit.
Okay, so they went overboard and it, but it's a heuristic. You play with it. You treat it like a hyperparameter. But one thing is, what is the yes, Sam, please go ahead, ask your question.
Yeah, but this bootstrapping would improve the R squared in regression, right?
Yes,
It will improve the R squared.
correct.
Ah,
But what happens? One major disadvantage of this application is that we can't explain explainability or description. Now, if it's a linear regression, now we can look at the weightage of if a single model, you can look at the coefficient of it and say whether this coefficient is very important or not, right? As long as the variables are standardized. But we cannot do that when we are looking at ensemble methods. We lose that that beauty of explainability. Prince, the way you are saying, asking whether when the data is large and should we go for ensemble or deep learning. Even in deep learning, you go for ensemble. And that's what I'm saying. Even when you go for deep learning, you'll do for ensemble. You'll go for ensemble. Okay. So essentially, deep learning is a different kind of a model to make a prediction. Okay. So again, all I'm saying is focus on different areas and build models for them. So that's the idea. So very simple idea. We will now go ahead and use similar idea on the features. On the features, not on the data points. What did we do? We randomly selected data points to do the bagging, bootstrap aggregating. But instead of that, what we want to do now is let the data points be the same. We will play with the variables to see which ones are important, to see how we can build a good model. That idea is called boosting. Okay, and I'm just going to give you the simple overall conceptual introduction to this. Okay, the details, they will be there in the file. You can go through them in your leisure, but we'll take a simple method of binary classification using decision trees. Okay, decision trees. So what does it mean? What we are going to do is we are going to start with some weak learner. Okay, what is meant by a weak learner? Some underfit model. Okay, say they don't learn properly. It's a weak learner. Okay, start with the underfit model, and then what you do is you find what are the data points for which this model does well and does not do well. Predicts correctly, predicts incorrectly. Now what you do, okay, the points that have been predicted incorrectly, I'm going to somehow make them more important and make the points for which the prediction was correct, I'm going to reduce the importance of them so that when you try a similar model again, this will balance out. Okay, so you get the idea. So let's see what is it that I'm doing. So let us say I'm starting with this kind of a data where we have 9 data points, demonstration purpose, triangles and circles. Okay, let's start with the binary. Let's start with the decision tree. Okay, you can clearly see we can have a decision tree which has one vertical line here and another horizontal line here. If you have that, the problem is solved. Okay, two nodes, but we want a weak learner, so we'll do one node at a time. Okay, one node at a time. So what do? I start with one node we build one node. Let's say this is the decision tree I have got. Anything above, anything below. How do I say? Anything above, I'm going to categorize it to be blue or circles. Anything below, I'm going to categorize them to be triangles. Okay. So whichever data points I categorized correctly, reduce the weightage. Whichever data points I categorized incorrectly, increase the weightage. So that means these two blue balls under this line will get more weights. Everything else will get less weights. Okay. So it will become like this. Blue balls become get more weights. These correctly classified balls and the triangles, they will get less weights. You can see they have visually shown that these are reduced in their weights. Okay. Now what I do, I build a tree. This tree is like this. Since these are the higher weights now, so the tree I've got is something like this. So these are classified correctly. And here, these three blue balls are classified incorrectly because the majority voting will go for the triangles. So what would happen? This circle, these two will get a slightly less weight. These three circles will get a slightly higher weight. These triangles will still get less weights, right? So they have reduced in size. These two are reduced in size. These three balls have increased in size, and these triangles now have still further reduced, right? So now I build a tree. Let's say I get this one, only one node. Okay, let's say I get this one. Okay, you remember how we build the decision tree, right? So you look for the information gain, all these different things. So you keep doing it, and then finally, what you do after a few iterations, you combine them all. You combine them all. And when you do that, you have a very clean prediction. This is a very silly example. So we got this from this tree, for example, you got one classification here, the second one is here, and the third one is here. Okay. So we got all these three correctly classified. So the accuracy here, the final ensemble, is better than any one of these individual ensembles. All these individual ensembles are underfits, that is weak predictors. Every time a weak prediction makes an error, the points with errors get boosted up, and the points with accurate predictions, they lose their importance, they go down. How much do I increase the weights of these points? How much do I decrease the weights of these points? That is the actual detail we have to worry about. Okay, so here is some mathematics for you. I'm not going to deal with this mathematics now, but it's you have to go through it slowly, steadily. But there is an algorithm. Okay, so where we essentially what we are going to do is we are going to look at the overall error, and then we are going to look at the error for these individual points and use that ratio kind of thing to calculate the weights for each one of them. And ratio by not by itself, but we are going to do some kind of a transformation, okay, like an exponential transformation to calculate the weights. Every time, first tree, the weights change by some amount. The second tree, the weights change by some other amount. How much? Every time you change it by this exponential function. And what goes inside the exponential? That's calculated by this error terms. Okay, so I'll let you go through this in your leisure, but there's a method to the madness of calculating the weights. So once you do that, you get, after a few iterations, you get a very clean way of getting the classification scheme. Okay, there are many different techniques of classification scheme. What we showed now is what is called adaptive boosting. But how do we get the correct weights? How do we travel through that? How do we modify the weights? Okay, this can be done by multiple methods, and that's one of the, obviously the well-known method is what's called the gradient method. Okay, and that's called the gradient boosting. I'm not going to go into the details of these techniques. They are much more involved, but just know that there are multiple different ways of calculating the weights in the boosting algorithm, and these go by the two common ones are adaptive grading and adaptive boosting and gradient boosting. The gradient boosting method, especially the XGBoost, light gradient boosting method, extreme gradient boosting method, and categorical boosting method, these are all different methods. People usually go for this technique called XGBoost. Okay? But the underlying idea is this: every time with a weak learner, when you predict incorrectly, increase the weights for those points for which prediction is wrong, and decrease the weights for those points for which the prediction is correct, and keep iterating. Okay? So that is called boosting method. So one method we saw how to deal with the sampling with replacement, called the bootstrap. The other one is learning from multiple weak learners by adjusting the weights for the errors of classification, and that's the boosting method. And people came up and asked questions about, no, why don't we deal with both the data and the variables in a single algorithm? And that kind of technique is what is called random forest. Okay. What does random forest do? It does the same thing that we do for bagging. You do the same thing for the variables also. Okay, but okay, it's not variables. We do the exact thing like bootstrapping there. What you do is you randomly select some variables. You randomly select some variables. You do a bootstrapping on the data set, and then use the random set of variables to build a model. Okay. So, and this, okay, this, now you see, this is like bringing together. It's a weak model. Why it's a weak model? Because we are not using all the features. We are using only a subset of the features. Okay. So it's like bringing the boosting as well as bagging together and smashing them and using building these ensemble methods. Okay. And this kind of technique is called random forest. In fact, there are quite a few faculty who vouch by random forest algorithm. They would blindly go to random forest and just use it, you know, without ruling out other methods. Okay? But it's a very powerful technique because what it does is it randomizes both the data as well as the features. Okay? And therefore it's building niche models for subspaces of the feature space. It's building niche. If you are looking at a subspace of feature space, and if you're using all the variables, you might end up overfitting this. Okay, so you might want to somehow, of course, since we are randomly selecting these variables, we might end up underfitting also. But on an average, okay, you are going to come somewhere in between these two, overfit and underfit. Therefore, for each one of these regions, you are going to have models that are tuned for those regions. And that's what this random